Hi, I'm Aamir Ali from Chalmers University of Technology in a Nordic country, Sweden. And I would like to thank the organizers for inviting me to give this talk, which is titled Thermally Driven Quantum Refrigerator Autonomously Resets Superconducting Qubit. So this is done in 22Q Lab, which is in Chalmers, led by Simone Gasparinetti and this experiment. And we had theory support from the group of Nicole Younger-Halpern in Maryland. So since it's in a distant country, I thought I would just introduce 22Q Lab. It's a lab which is dedicated to using superconducting circuits to explore several research directions, which spans a very broad range, going from fundamental to applied. And so what I will be talking about is quantum thermodynamics, which is fundamental, but we also do quantum computing and in fact also develop hardware. For example, we have invented some microwave filters, which has led to a spin-off in a Sweden quantum company. We are still hiring, so if anybody's interested, you can get in touch for this PhD and postdoc positions with Simone, or you could also talk to me. So the motivation behind this work is that we think that quantum thermodynamics should be more useful. And in the community, we have already been talking a lot about looking for quantum advantages in thermodynamics. So for example, how would you beat any classical machine in terms of power output, charging speed, or precision? Whereas the other aspect we were concerned about is how do you deploy this in practical applications? And to this end, we started looking into doing qubit reset with a quantum thermal machine. So qubit reset is a very important process. It's one of the DiVincenzo's criteria for quantum computing that you should be able to initialize to a good ground state. And you would think that should be easy. If you leave the qubit, it will ultimately decay to the ground state. But actually, it's more complicated than that. Typically, they are always getting excited by the environment. And if you leave it, it will typically go to a ground state population, which is 97 to 99%, not really 100%. And that's what could lead to errors in quantum computing. So there are many smart ways of dealing with this. So for example, there's something called active reset, where you keep on measuring the qubit, and every time you find it in the excited state, you flip it back to ground state. Or you could do something called unconditional reset, where you could have a switch which keeps on, where you would connect the qubit to a very cold mode to quickly reset it to ground state, and then disconnect for your calculations. But all of this requires very heavy quantum computing resources. So specifically, you need some coherent drives to do this. And what we were asking is, could we do it with a quantum thermal machine with minimal thermodynamic resources, which is basically just naturally available thermal baths? So this is what the motivation behind this work. And to do this, we look at something called quantum absorption refrigerator. So typically, refrigeration requires a source of free energy because you're moving heat from a cold bath to a hot bath. So you typically have to do some kind of thermodynamic work to do that. But what is special about absorption refrigerators is that instead of doing thermodynamic work, you can drive it by another flow of heat, a natural flow of heat going from hot to cold. And since we have been talking a lot about harvesting energy, it's actually something which is used a lot in the macroscopic world. For example, in factories where you have generated a lot of excess heat, you could use that excess heat to drive some refrigeration of another important process. So what does the quantum version of that looks like? So it would have three quantum objects, and three coupled to their three baths. And here we want to cool down the blue one, the reservoir, to be cooled. So to drive the heat from the blue one to the purple one, which is accepting that heat, we take advantage of a third bath, which is the hottest one. And from there, we have a natural flow of heat going from the hottest one to the heat acceptor, which drives this cooling process. So this quantum version has already been realized in a proof of principle experiment with trapped ions back in 2019. And however, it's not really used for something useful. So what we went on to do is to realize this with superconducting circuits and do something useful, which is qubit reset in this case. So the scheme in our experiment works as follows. So you want to do qubit reset. We have three qubits over here. So two of them are coupled to controlled heat reservoirs. And this together forms the quantum thermal machine. And its job is to cool down this target qubit, which is undesirably coupled to an uncontrolled reservoir. So it's all hot, which is the case in our target qubit we want to cool down, and we use the thermal machine to cool it down. So another important aspect is that these are all coupled to each other with a three-body interaction. All right, so these three are coupled with this Hamiltonian. So the way it works is that, let's say the target qubit T, the target qubit, is excited. Then nothing really happens. However, when you also have the qubit H excited, all right, and you have a resonance condition such that the sum of these two transition energies is equal to the transition energy of the middle, the blue one, then with the help of this Hamiltonian process, you can exchange this excitation in such a way that these two go into the blue one, and then that is rapidly dissipated away into the blue bath. So this is, at the end of this, we got rid of the excitation in the qubit, the green qubit over here. This is how we reset this qubit. So to make this work, we need two ingredients. So one of them is the control bath, that you should be able to control the bath of this quantum thermal machine. And the other one is to engineer this three-body interaction. So the first one we do by using microwave waveguides, which are coupled to this qubit. So over here is such a waveguide coupled to this qubit. And what we need to do in order to let it be a heat bath is to populate this with black body radiation, basically photons, which have a spectral density same as you would see in a black body. And what is more, there's one more step that we could do, and that is that, or one more observation is that only the spectral profile around the transition energy of this qubit matters. You don't really need it to be going over all frequencies. You only need it around the frequency of the qubit. So to do this, we have a artificial noise source, where we generate that such a spectral profile, but only over a narrow range which is relevant to that qubit, and then we send it and populate the waveguide with that radiation, which acts as the heat path. And this is something we have done in a previous work here in PRX, where we basically did a thermometry of that generated radiation using the qubit itself, which we call quasi-thermal radiation, because it looks like thermal radiation, but only over a small bandwidth. And we also saw in this work that we have a very good agreement between the synthesized and the natural thermal bath. So we know that this part works. Now we come to the refrigerator part. So over here, this is how we design our device, the scheme. So we have these two qubits which I mentioned, which are coupled to the microwave waveguides, which will act as the baths. And they are all coupled to the third qubit, the green qubit over here, which is the target qubit we want to reset. It's coupled to, also dispersively coupled to a resonator with which we do the measurement to look at the population of that target qubit. So we need this three-body interaction. But what is slightly different over here is that we have actually there are four-wave mixing happening over here. So we have an excitation from the green qubit and the red qubit being exchanged for a double excitation in the blue one. So this is why the Hamiltonian looks like A1, A2 dagger, A2 dagger, A3, which is basically extending these two single excitation for a double excitation. And the way we achieve this with superconducting circuits is in a standard transmon device, a device made of transmon over here, which is this plus cross shapes. These are the qubits. We have a Josephson junction, which introduces nonlinear mixing between these modes. So effectively, we have a cosine function over here of all these modes inside this that can ultimately lead to this Hamiltonian term, which we need for the three-body interaction, as long as we satisfy the resonance condition, which is basically that the sum of these transition energies has to equal the double excitation in the blue qubit. We have to make sure this resonance condition is satisfied. So that is why we make one of this qubit frequency tunable, so that we can tune omega 2 until we can satisfy the resonance condition. So, and the range of frequencies we are talking about is what is standard in quantum computing with superconducting circuits, which is in the range of 3.7 gigahertz to 6 gigahertz. And the omega 3 is the one we are trying to cool down. So first, I want to show you that we do engineer this three-body interaction. It's not very common to get that, but in circuit QED, it's something you can engineer. So the way we do it is we first excite the qubit 3 deliberately with the pi pulse, And then with a small coherent drive on the qubit 1, we slightly excite the red qubit. And now we want to see whether there's an effect, whether there's a, after having both of them excited, do they go into the blue qubit, which I will find out by looking at the population or what is the state of the green qubit over here. So excite qubit 3, resonantly drive qubit 1, and then measure qubit 3. And we repeat this while varying the frequency of the qubit 2 to look for the resonance condition. So this is that experimental plot. So over here in the 2D plot, in the x-axis, we are changing the frequency of qubit 1. On the y-axis, we're changing the frequency of qubit 2. And we are measuring the state of the qubit 3, the third body. And finally, at the center where we have the resonance matching, we hit the bullseye. And we see that qubit 3 population decays rapidly over here when the resonance condition is satisfied. So now we park our frequencies at the bullseye and look at what the population of qubit 3 looks like. So this is that plot where we find that as we keep on increasing the magnitude of the drive, so the more excited the red qubit is, the more likely this qubit is going to get reset. And that is what we see, the state readout goes towards ground state when omega 2, the drive of the qubit 1, is strong enough. So this is where we show that we do have this three-body interaction between this. Now comes the part where we operate this like a refrigerator. And in this case, now what we would do is, again, deliberately excite qubit 3. But now we will be sending out the artificial radiation I mentioned in the beginning, which acts like a thermal bath to qubit 1, which appears like this noise, so that we now have qubit 1 at a thermally excited state. So yes, so this is the experimental result. We look at this different plots as a function of NH, which is the number of average photons sent to the hot qubit, or the hot bath. So here, when we have zero number of photons, zero hot photons over here, we find that the population of the qubit 3 decays in its natural relaxation rate, which is about 17 microseconds. It's a standard number in superconducting circuit. However, as we start increasing the number of hot photons in the hot bath and therefore exciting the qubit 1, we see that the rate at which qubit 3 decays becomes faster. In fact, by the time we have about 21 photons in the hot bath, we find that the relaxation time of qubit 3 drops by a factor of 70. So this is the one where we see a very sharp drop. All right, and then it comes down, saturates to a very low value. So what is interesting to note is that it goes much below these two dotted lines. So the red one is the default thermal state of qubit 3, which is basically if you had left it just by itself, it will actually go to a population of about 2.3% excited state. On the other hand, if we had coupled the qubit 3 forcefully to the coldest bath around, which is the bath for qubit 2, 45 millikelvin, it would have been at the blue line. However, we are cooling it down to much lower than all the baths available. And if we look at what that is, so the steady state population is about 0.0005. If we convert that to an effective temperature, that turns out to be about 23.5 millikelvin. And the coldest bath around is 45 millikelvin, which means that we are cooling it below all the temperatures that is available. That's the power of this refrigerator. Unfortunately, the reset time is not very rapid. You would have liked it to be in some tens or hundreds of nanoseconds. But in this refrigerator, we have it about 1.6 microseconds. What is also important to look at this is that this is a completely autonomous refrigeration, which means that you don't really have to send any coherent drives. In this case, we make sure that the qubit 1 is connected to a hot bath, but we can show that there are some ways in which you can implement this in a setup where you really don't have to do anything, and the qubit will get autonomously refrigerated to a very good ground state. So if you look at how does it compare to the state of the art, so these are some of the plots, some of the other popular protocols that are used. We are somewhere really low on the residual population. But if we leave it, or if we go outside this chart, somewhere over here and low enough, high enough duration, we'll find that our residual population is better than all the other reported values in the literature. So in summary, what I have shown you is that we have demonstrated a superconducting quantum absorption refrigerator, which is useful. It does qubit reset, and it's also autonomous. Its performance is competitive with the state of the art. And it's a very resource-efficient approach to doing a quantum computing task. So this is a useful task done with a quantum thermal machine. And what I mentioned earlier, so you could also think about connecting these waveguides. So over here, the waveguides, which are where we send artificial noise, you could actually connect it to existing plates in our dilution refrigerator where we do this experiment. The device is kept over here, but you have a few different temperature plates at different temperatures. So we can connect these waveguides permanently hardwired to these plates, and that will drive the refrigeration, so you really don't have to do anything. So in that sense, it's very resource efficient. So this is also another aspect of this, is that this is a very holistic way of using circuit QED and thermal waveguides for studies in quantum thermodynamics. Thank you.
Thank you very much. We are running out of time, so maybe we have time for just one question. And yeah, maybe.
You can use this one.
No, there's another question back there.
I don't need two microphones. Hi. Nice to see your talk a second time. Now I have a question. Actually, could you elaborate a little bit on the resource efficiency of your scheme with respect to the basic, passive scheme, just coupling it to a resonant zero temperature bath? I have not really understood to which extent it's more resource efficient.
Yeah, can I get to my slides? Can I vary my slide? So, yeah, the idea is that when we do qubit reset, we typically, as I mentioned in those protocols, you need to use some coherent drives, microwave tones, and that is not given naturally. That is not available naturally.
Not
it's something
in
we
the passive
synthesize.
case.
Sorry?
Not in the passive case. You don't use a tone in the passive case. You just
in the
use
passive case,
spontaneous emission.
where I mentioned the switch, where I mentioned.
Oh, so there is a switch to couple a resonant waveguide on demand to your qubit, is that so?
Yeah. So you still need some sort of a parametric drive to turn on that switch.
Okay.
So you always need some coherent drive, and that's
Okay.
like a laser. On the other hand, what I meant by minimal resources is thermal baths are considered the minimal resources available.
Right. Okay. So it comes from an assumption of what is a free resource and what is not.
Yeah.
To say it's resource efficient, but there is no quantitative estimation of to which extent it's more resource efficient.
Between the two different protocols.
Yeah.
No, not in that sense. I was
Okay.
mentioning the thermodynamic sense.
Okay.
Yeah.
Thanks.